So, so far now in this course, we have learned different biasing techniques and different ways of realizing an amplifier, common source, common drain, common gate, and all these things. And we are pretty much seen different types of transistors like MOS transistor, bipolar transistor, and in the MOS transistor, we have seen PNP, NPN, and how their one circuit can be converted from NMOS to PMOS, and things like that. And now we are in a position to understand amplifier circuits that involves more than one transistor. So far we have been dealing with amplifier circuits with one transistor. At max we have used two in the case of current mirror bias and so on like that. But now we'll discuss certain cases where you have more than one transistor in an amplifier circuit. So essentially what we have been doing so far is we have given the input to one, we have given the signal input to one of the transistors, even if it had two transistors in current mirror bias and so on. But then now we'll see how to give your signal to more than one transistor, and then such type of circuits, how it works and all these things. A very common example of such a case is your opamp. Say for example, this is your opamp, okay, and let's say this is V1 and this is V2 and this is V out, okay. And so obviously you will give one input to one of the terminals. Say V1 will take one input and then V2 will take another input, and then you will get some output at the V out. And of course you will have feedback around the op-amp, and we have seen different types of circuits. In particular we have seen what is called the voltage control voltage source using op-amp, and the current control voltage source using op-amp. We have seen it in detail, okay. And we know that this op-amp, in the model of the op-amp or the incremental picture of the op-amp will look something like this. This is V1 and V2, and this difference is Vd, which is equal to V1 minus V2, okay. And you have, this is a voltage control voltage source. Op-amp is itself, it's a voltage control voltage source, and this is V out, and this is the voltage source controlled by this different voltage Vd, and then it will be A0 times Vd, okay. And A0 is the gain, and A0 tending to infinity, we call it as an ideal op-amp. We have seen this right? And how it is, this is just a model for an op-amp. Just like you have a transistor represented in this symbol, okay, which is your drain and source and gate. You have an op-amp represented by this symbol, okay. But how it is realized is something that we will see now, okay. So basically the main quality as far as an op-amp is concerned, that if suppose I give you a circuit, say for example I give you a circuit like this, say this is R, and this is K minus 1 times R, okay. And let's say this resistor is not there. Even if it is there, it doesn't matter, but then let's say it is not there, and then this voltage will be V out by K, and if you give some V in here, you will equate V in is equal to V out by K, and you will say this amplifier has a gain of K, okay. That is how you will realize, you will try to analyze this op-amp circuit, or rather the ideal op-amp circuit, okay. So now basically what it does, it amplifies the difference between these two inputs, okay. And that when this gain tends to infinity, we have seen a picture where when this gain, this is the gain, say, okay, and the slope is essentially the gain, and you will have another case where this intersection point, this will be the feedback equation, and this will be the forward path equation, and this intersection point is essentially my Vd. And if the gain tends to infinity, then this point will move here. If this slope is much higher, it will move up, and then this point will move up in this line and it will touch here, and Vd will tend to 0. This we have seen, right? But then how do we realize this is a question, meaning if I want to realize something like this, okay, so basically what I want to realize is I want to realize a situation where I can actually give V1 and V2 as two inputs, okay, and then looking into this side, I should have an input resistance or input impedance to be infinity, because that is one of the major qualities of an op-amp, because it should not draw any current, okay, and when connected in negative feedback it should not draw any current, and the difference voltage, if I take the difference voltage Vd is equal to V1 minus V2, okay, this is the different voltage, let us say, and then I should have a voltage source here, or an output voltage is what I need, V out should be controlled by this different voltage alone, meaning I can have V1 and V2. V1 and V2 can have any combination. I mean, instead of V1 minus V2, I could have V1 plus V2, or I could have some factor of alpha times V1 plus alpha times V2, or alpha times V1 minus alpha times V2. Anything could be here, okay. But then I specifically want only V1 minus V2, because that is the quality of the op-amp, and that should be controlling this voltage source by this gain A0, okay, A0 times Vd. Okay, so I am only concerned about the case where you give two inputs at the two voltages at the input, and I need a box, okay, where I give two voltages at the input V1 and V2, and this box should somehow consider only V1 minus V2, okay, some A0 times V1 minus V2 at the output. This is what I want, and I have to realize it somehow. And so far we have been spending time understanding amplifier circuits, single transistor amplifier circuits in very much detail. So obviously we are going to use an a transistor to build this, okay, that is the motivation I want to give. So basically in the rest of the course we'll be seeing how to implement op-amp, or at least a single stage op-amp, because we will not go into very much details. A single stage op-amp, at least the first stage of the op-amp, that is what I mean, okay. So op-amp, single stage op-amp using MOS transistor. So this is the motivation, this is what we will be doing, okay. But then how do we do it is another question, okay. Let's see, say for example, let me put it down here. See, if you take a MOS transistor, if I take a MOS transistor, gate, drain and source, see, sometimes because we have been now very much familiar with MOSFET and its small signal equivalent, sometimes I'll just draw the MOS transistor, and then by whatever we are going to use it for, you should understand whether we are talking about small signal or large signal, okay. So because it's really difficult to keep drawing this structure again and again, and given that we have spent so much time understanding the small signal models, we draw the transistor, basically this should come to your mind in the small signal incremental picture, okay. So let me just illustrate it. This is my VGS in the small signal picture. Similarly, VGS is I have here source and GM VGS, right? We know this. Now if you see, MOS transistor in itself will actually respond only to the difference between the inputs G and S. Say for example, this is my VG input, this is my VS input. Let's say my source is not at ground, okay. I am not explicitly grounded the source, it is not at ground, it has some potential, let's say, okay. So this is my VS and this is my VG, and VGS is equal to VG minus VS, okay. And you see this current source ID, this ID is nothing but GM times VG minus VS, okay. So you see, it's actually the difference between the input voltage VG and other voltage VS, and multiplied by some gain, here it is a trans conductance, is your output current, and I pass this current through some resistor, I am going to get some output voltage, which is also a response to only the difference between the signal. This is what exactly I wanted, okay. But why can't we use just a single transistor? The reason is the following. Say I use a single transistor, okay. Now I use a single transistor. So here I have to give one input, let's say V1, okay. This is one input. Instead of VG I am giving V1 here, and instead of this is gate, this is source, instead of Vs, I am going to give V2. Okay, these two inputs I have given. Okay, now for now, you just don't worry about the drain potential. We'll see what will happen to the drain. As of now, you just imagine the drain is somewhere at some DC bias, so that it's properly in saturation, and then incrementally it will be grounded. It doesn't matter. If I need some gain, I can actually put some resistor there or put a load and try to get the gain out of it. But as far as this argument is concerned, I have given one input here and another input here, so I will have the small signal current flowing in this way, okay, which will be GM VG minus Vs, VG minus Vs, which is nothing but GM V1 minus V2 in this case, right? Because the VG is V1, Vs is V2. So pretty much it. So I wanted the difference voltage. So VD is nothing but VGS. So GM VGS I have as a current, and if I take this particular current and pass it through a resistor, so what will happen? This will have some voltage. This node will have some potential, and that potential is this one. Okay, it's pretty much it. Just that it will be negative here and it is positive here. It's okay. That is still okay. Okay, but the major problem, as far as realizing an op-amp is concerned, the point is, if you look in from both the inputs, either from the Vin side or from the perspective of V2, your input impedance should be infinity. Okay, now if you take a MOS transistor and look at it from the input side VG, okay, as far as VG is concerned, because VG, see, what do I mean by that? V1 will be applied. So as far as you take an op-amp, now if I talk about, if I say this is V1, it's essentially a voltage source of value V1 connected to ground, this point and ground. Okay, so if you try to see the impedance looking in this side from this point and ground, it is infinity. And as far as V2 is concerned, it's again a voltage source connected from this point and ground. And when you look in this side from from the perspective of V2, again it is infinity. Okay, input impedance. Now you take a MOS transistor, you connect an input, okay, VG, from this point and ground. You look in this side, input impedance is infinity. Okay, good. But then you connect Vs, it will be this side, right? You connect a Vs here. So the problem here is this Vs is essentially shorted all throughout. So you put a Vs here, it means Vs is here also. Okay, I hope you understand, because here, as far as op-amp is concerned, one terminal is always grounded of the voltage source. Okay, so it is left open this side, but here it is completely shorted. So source is common between input and output. So you connect a voltage source here, Vs, let's say, and you look in this side, right? So because it is shorted, you look in this side, you will have a resistance of 1 over GM. We have done this multiple times. You look in this side, because GM VGS is flowing here, you connect some Vs here, and you will have input impedance of Rin will be equal to 1 over GM. Okay, for V2 is concerned, as far as V2 is concerned, that is applied to the source, you will have 1 over GM as Rin. Okay, so what is the problem? GM is a large number. Okay, as far as the MOS transistor is concerned, GM will be a pretty large number, and once you have 1 over GM, this value will become smaller. Okay, but ideally I want it to be larger. Okay, ideally I want a large number, but then I am not getting it. Okay, I want Rin to be infinity ideally. Okay, but then I am not getting it. That is the whole problem, and I cannot have an op-amp where input impedance is some value for V2 and some it's not something for V1. So what will be the problem if I have something like that? Say, as far as I apply V1, some V1 I apply, okay, this V1 will directly appear at this point as V1 itself, because input impedance is infinity, while when I apply V2, so I will have V1 here, but then when I apply V2 here, this 1 over GM is input impedance, so this will occur, this will cause some drop to occur from V2. Okay, so V2 will not appear here as V2 itself. V2 will be some fraction of V2, and then I will not get V1 minus V2. That is the whole point. Okay, because I want V1 minus V2 exactly. I don't want any fraction of V1 and fraction of V2. I want exactly V1 minus V2, and that is only possible if I have looking in impedance from input side, as from V1 side and V2 side, both are infinity, but then here it is infinity and here it is 1 over gm. And so I want to realize a situation where looking from both the side I need infinity as the input impedance. Okay, I hope you understand the problem, and now we'll look at the solution in the next lecture.